So picture this. It's 1987, and a computer actually manages to translate a sentence from English to Spanish using, an artificial neural network.
Right, which was a massive deal at the time.
Huge deal. But the catch, the network's entire vocabulary was exactly 31 words.
Yeah, just 31.
And it took, decades of waiting for computer hardware to finally catch up to the sheer complexity of the math required to get past those 31 words. So, welcome to today's deep dive. We are taking you on a really personalized journey to understand how the translation apps on your phone actually work.
It's a fascinating evolution.
It really is. Our mission today is to sort of demystify the mechanics of how computers learn to translate human languages. We're tracking that whole evolution from those clunky 1980s experiments to today's massive AI models and really trying to figure out what is actually happening when you click translate on a web page.
Because it's definitely not what most people think.
Exactly. Okay, let's unpack this. We all generally understand how a computer processes binary, right? Just ones and zeros. But how do we translate the abstract, messy human concept of meaning into something a machine can calculate? I mean, how is neural machine translation, or NMT, as we'll call it, how is that different from just, holding a massive digital dictionary and swapping the words out one by one?
Well, that dictionary swap idea is probably the most common misconception.
Yeah.
But human language just simply defies that kind of one-to-one mapping.
Right, because of grammar and stuff.
Exactly. Grammar, syntax, and just context fundamentally change meaning. So neural machine translation doesn't swap words at all. It uses an artificial neural network to predict the probability of a sequence of words. It's usually modeling entire sentences in a single integrated model.
Wow, entire sentences at once.
Yeah. So instead of looking at isolated puzzle pieces, it processes the entire picture to predict the mathematically most probable translation.
Okay, so that makes it basically a game of probabilities. Given a specific Spanish sentence, the system just calculates the most statistically likely English equivalent.
Precisely. And because it models the whole sentence, NMT has really become the dominant approach in the industry. I mean, for high-resource languages.
Like English or Spanish.
Right, English, Spanish, French.
Yeah.
Languages where we have literal mountains of high-quality bilingual text to train the system. For those, NMT can genuinely rival human translation.
But it's not perfect everywhere, right?
No, definitely not. It still struggles with low-resource languages where that training data is scarce.
Yeah.
And, even then, it can occasionally produce translations that are just overly literal.
Right, a bit robotic. Well, to understand why it succeeds or why it sometimes produces that rigid translation, we really need to dig into how a neural network processes a sentence in the first place. Because we are dealing with machines that don't inherently understand concepts like sarcasm or urgency. They just process numbers.
Yeah, they process everything with vector mathematics.
Vector mathematics. Okay, break that down for me.
Sure. So most NMT models use what's called an encoder-decoder architecture. The first step is the encoder network. When you feed a source sentence into the system, the encoder doesn't actually see words. It converts those words into a mathematical vector.
Okay.
You can think of this as mapping every single word to a specific coordinate in a really high-dimensional mathematical space.
So instead of a flat paper map with an X and Y axis, we are talking about a space with hundreds or even thousands of dimensions.
Exactly.
And the system plots a word like, say, king at a specific coordinate, and then queen ends up plotted geometrically right next to it because their semantic meanings are so similar.
Yes, that's it perfectly. The distance and the direction between these coordinates represent their relationships. The vector space essentially captures the context.
Oh, that's wild.
It is. Like if you use the word bank in a sentence about a river, its vector coordinates are going to sit near words like water and shore. But if you use bank in a sentence about a mortgage, its coordinates dynamically shift to sit near money and vault. So the encoder processes the entire source sentence and produces a matrix of these vectors.
Which is basically a complex mathematical representation of the entire thought.
Exactly.
Okay, so the encoder takes the source thought, maps it out as coordinates in this 1,000-dimensional space, and then hands that map over to the next system.
Right, that map is passed to the decoder network.
Okay, the decoder.
Yeah, the decoder takes that mathematical representation and produces the target words, usually generating them just one at a time. And what's fascinating here is that the decoding process is autoregressive.
Autoregressive, meaning what exactly?
It means it relies on its own previously predicted tokens to guess the next one. So it generates the first word, factors that word into its calculations, and then uses it to guess the second word.
Oh, I see.
Then it uses the first and second words to guess the third, and it only stops when it finally generates a special end-of-sentence token.
Okay, it's like walking across a stream on stepping stones.
Oh, that's a good way to put it.
Yeah, like each step you take determines where you are balanced enough to step next. You have to commit to your current step, but you're constantly looking back at the bank you came from the source sentence, right?
Right.
To make sure you're still heading in the right direction to reach the other side.
That's a great analogy, because if you take a misguided step early on, your entire path across that stream shifts. You're either forced to correct course or you just end up in the wrong place entirely.
Right.
The autoregressive nature means every single output relies completely on the structural integrity of the previous output.
Okay, so if the underlying math, this whole encoder-decoder vector mapping thing, if it's so elegant, why did we spend the early 2000s dealing with those notoriously terrible robotic internet translations?
Well, that comes down to the hardware.
Right, because the timeline here is fascinating.
Yeah.
We established that Robert B. Allen was running feed-forward neural networks to translate English to Spanish way back in 1987.
Yeah, but Allen's 1987 model was just a proof of concept. The network's input and output layers had to be specifically sized for the longest possible sentence, because those early networks couldn't handle arbitrary varying sentence lengths.
Right.
But his summary actually outlined the dual encoder-decoder model we still use today.
Which is crazy. And the momentum continued in the 1990s, right? Lonnie Chrisman developed those RAM networks in 1991 that could encode variable-length sentences into fixed-size representations.
Yes, and then Forcada and Yanko in 1997.
Right. They directly trained a source encoder and target decoder. So they literally had the theoretical architecture mapped out before the turn of the millennium.
They had the blueprint, absolutely, but they lacked the raw material.
The computing power.
Exactly. The computing resources of the 1990s were just completely insufficient to process the massive bilingual data sets required to train a neural network on real-world texts. The computational complexity of calculating those high-dimensional vectors across millions of parameters, it was just way too high for the processors of that era.
It sounds like trying to sequence the human genome using an abacus or something.
Yeah, basically.
The math is theoretically sound, but you just don't have the speed or the memory to actually finish the calculation in any kind of usable time frame.
Right. And that hardware limitation forced the entire industry to pivot. So for 2 decades, a completely different method called statistical machine translation, or SMT, became the standard.
Okay, SMT.
Yeah, SMT abandoned neural networks entirely. Instead, it used these massive statistical models that analyzed huge volumes of text to map the probabilities of specific phrases, which they called n-grams.
So it didn't actually understand the semantic meaning of a word in a vector space like we talked about.
No, not at all. It just counted how often word A appeared next to word B.
Well, that completely explains why early internet translations felt so disjointed. It was essentially looking up a phrase, finding the most statistically common replacement, and just pasting it in without understanding the overarching thought of the paragraph.
Exactly. But SMT was the best we could do with the hardware constraints of the time.
So what changed?
Well, by 2013 and 2014, processors and specialized hardware, specifically GPUs, had finally caught up. And we saw the breakthrough of end-to-end neural machine translation, specifically the Seq2-Seq, or sequence-to-sequence models.
Right.
Researchers like Couchbrenner and Blunsum utilized convolutional neural networks, which basically apply sliding mathematical filters over the text to encode the source. And simultaneously, Cho and Sutskever utilized recurrent neural networks, or RNNs.
And those process data sequentially, right? Maintaining a kind of internal memory state.
Yes, exactly.
Wait, let me pause you there. If the encoder is compressing a 50-word sentence into the exact same fixed-size mathematical box as a 3-word sentence, doesn't it run out of room?
Oh, that's a very perceptive question.
Like, wouldn't it sort of forget the beginning of the paragraph by the time it reaches the end?
You've hit on the exact phenomenon researchers call computational amnesia.
Computational amnesia, that's a great term.
It is. Squeezing a long, complex sentence into a single fixed-length vector created a really severe bottleneck. The model performed exceptionally well on short phrases, but the translation quality just plummeted on longer texts because that early context was overwritten or diluted by the time the encoder reached the end of the sentence.
So how do you retain the context of a massive paragraph without just overflowing the mathematical limits of the system?
You have to change how the decoder looks at the information.
Okay.
So in 2014, Bahdanau and his colleagues introduced the attention mechanism.
Attention.
Yes. Instead of forcing the encoder to squeeze the entire source sentence into one rigid box, the attention mechanism allows the decoder to look back at the original source sentence at every single step of the decoding process.
Oh, wow.
It calculates a dynamic representation that focuses or, pays attention to different specific words in the source sentence depending on what target word it is currently trying to translate.
Okay, so if the system is translating a long paragraph about, I don't know, a red sports car driving dangerously fast down a mountain.
Sure. When the decoder gets to the specific moment where it needs to output the word for car, the attention mechanism acts like a spotlight.
Yes.
It highlights the vectors for red, sports, and fast in the source sentence to ensure the context is perfectly aligned for that exact microsecond of translation.
That's it, exactly. It mathematically weighs the relevance of every single source word against the current target word being generated. And this completely eradicated that fixed vector bottleneck we talked about.
That's incredible.
The real-world impact was immediate and just massive. By 2015, Baidu had launched the first large-scale NMT system. And then in 2016, Google followed with the Google Neural Machine Translation System.
Okay, here's where it gets really interesting. The attention mechanism was initially designed as a patch, right?
Yeah, pretty much.
It was an add-on applied to those recurrent neural networks to cure their computational amnesia. But then researchers asked, well, what would happen if you stripped away the RNNs entirely and made attention the actual core foundation of the architecture? And that inquiry led directly to the transformer, which was introduced by Vaswani and colleagues in 2017.
The transformer.
Yes. The defining feature of the transformer is self-attention. Previous RNN models process data strictly sequentially. So word 1, then word 2, then word 3.
Right.
The transformer discards the recurrent loops completely. Its encoder and decoder layers use self-attention to weigh and transform the entire sequence of words simultaneously. Everything is processed in parallel.
Wait, hold on. If it processes the entire sentence in parallel, reading all the words at the exact same time, how does it know the grammar? Like, how does it differentiate between the dog bit the man and the man bit the dog if it doesn't process the order of the words?
That is the inherent challenge of parallel processing. To solve this, the transformer uses explicit positional encoding.
Positional encoding.
Right. Before the words are fed into the self-attention layers, the system adds a unique mathematical timestamp, usually using a mix of sine and cosine functions to each word's vector.
Oh, clever.
Yeah, this modifies the vector's coordinates just enough to embed its precise location in the sentence. So the model reads everything at once, but it reads those mathematical name tags to reconstruct the exact syntax and order.
So it basically retains the massive speed advantage of parallel processing without sacrificing the grammar.
Exactly.
And this architecture officially killed off the old statistical machine translation models, didn't it?
It did. NMT outclassed SMT across the board. First, because NMT uses continuous vector representations, it solved the sparsity issue.
Sparsity.
Yeah, in SMT, if a word was rare and didn't have enough statistical data, the system simply failed to translate it. It just threw an error or gave up. But in NMP, even a rare word is plotted somewhere in that high-dimensional space, allowing the model to infer its meaning based on its proximity to more common words.
Wow, so it understands the concept of the rare word, even if it hasn't seen it a million times.
Exactly. Second, SMT relied on those n-grams chunks of a few words, which created a hard cutoff. If you used a 5-gram model, it was physically incapable of remembering a grammatical rule established 6 words ago.
Right, because its memory was only 5 words long.
Right. But the transformer, using self-attention, has no hard cutoff. It can connect a pronoun at the very end of a paragraph directly back to a noun at the very beginning.
That's a game changer.
And finally, despite the incredibly complex math, an NMT model actually uses significantly less memory than the massive, sprawling databases required for a high-level statistical model.
Okay, so we have this incredibly powerful architecture in the transformer, but an architecture is essentially an empty brain. How do we train a matrix of parameters to know what a fluent translation actually looks like?
Training an NMT model relies on a metric called cross-entropy loss.
Cross-entropy loss. Sounds intense.
It's really cool, actually. You feed the untrained model a massive data set of bilingual sentences. So say an English source and its perfect Spanish translation. The model attempts to translate the English sentence. And in the beginning, its prediction is essentially just random noise.
Right, doesn't know anything yet.
Exactly.
Yeah.
Cross-entropy loss is a mathematical function that calculates exactly how far off the model's prediction was from the ground truth target. It outputs a probability distribution over the entire vocabulary, and the loss function measures the distance between the model's confident guess and the actual correct word.
So the system tries, fails catastrophically, and the cross-entropy math quantifies the exact magnitude and direction of that failure.
Spot on. Once the failure is quantified, the model uses an algorithm called stochastic gradient descent. It calculates the slope of the error and iteratively adjusts its billions of internal parameters, the dials and knobs of the neural network, downhill toward zero error. It processes the data in small chunks called mini-batches, constantly tweaking the vector space to maximize the probability that it produces the exact target sentences.
That makes sense.
But if we connect this to the bigger picture, the autoregressive nature of the decoder creates a massive hurdle during this training phase.
Because it relies on its own past guesses.
Yes, the decoder uses its own previous output to guess the next word. If the untrained model gets the very first word wrong, it feeds that incorrect word back into itself, virtually guaranteeing that the second, third, and fourth words will also be completely wrong.
Okay, I get it. It's like a piano teacher sitting next to a student who is learning a complex chord progression.
Okay, I like where this is going.
If the student hits the very first chord wrong, they might try to play the rest of the song in that wrong key, right? They're building an entire sequence of bad muscle memory based on one initial mistake. To fix this, we use a technique called teacher forcing. Like, the piano teacher physically forces the student's hands onto the correct first chord and says, now from this correct position, play the next chord. The teacher forces them to the right starting point for every single step so they learn the correct overarching sequence.
That is a brilliant analogy, yes. During training, regardless of what garbage the model actually predicts, the system forcibly feeds the correct ground truth token from the training data back in as the input for the next step.
So it can't spiral.
Right. Teacher forcing ensures the model doesn't spiral into compounding errors, allowing it to efficiently learn the mapping of the vector space.
Incredible. Okay, so up to this point, we focus strictly on dedicated NMT models, right? Systems explicitly designed with an encoder and a decoder trained on parallel bilingual datasets to do one specific job.
Right, translation.
But the landscape has shifted radically in just the last few years with the rise of generative large language models, or LLMs, like GPT-3 and GPT-4.
It really has. The architecture of a generative LLM is fundamentally different from a dedicated NMT system.
How so?
Well, LLMs are typically decoder-only models. They completely discard the encoder network we talked about. And more importantly, they are not explicitly trained on parallel translation datasets.
Wait.
Really,
Yeah.
They are trained on a broader language modeling objective. They just simply predict the next logical word in a sequence drawn from a massive internet-scale dataset, the vast majority of which is in English.
That's wild, because there was a 2023 study by Hendy and colleagues that demonstrated that despite not being trained specifically to translate, these generative LLMs can produce highly fluent competitive translations in a zero-shot setting.
Yes.
Meaning you don't feed them bilingual examples, right? You just prompt them to translate this, and they do. How is an autocomplete engine executing high-level translations?
Unprecedented scale. To compete with a dedicated translation system, these LLMs utilize a brute force approach of sheer size. By ingesting trillions of words across multiple languages during pre-training, the model develops an internal cross-lingual representation of language.
So it's not translating like the old models.
Not exactly, no.
Yeah.
It isn't translating in the traditional sense. It is mathematically predicting that the most logical continuation of the sequence, translate hello to French, is the word bonjour.
Wow. And the scale comparison is just staggering. I mean, MBART, which is a dedicated NMT model heavily fine-tuned specifically for translation, uses roughly 680 million parameters.
Which is a lot.
It is. The original Transformer model from 2017 used 213 million, but GPT-3 utilizes 175 billion parameters.
Yeah, the difference in magnitude means generative LLMs are computationally exorbitant to train and to run compared to an elegant, dedicated NMT system.
So what does this all mean for you, listening right now? We started in 1987 with a neural network that could barely juggle 31 words because the hardware was decades behind the math. We suffered through the statistical, phrase-swapping era of early internet translations.
We all remember those?
Oh, yeah. Then the hardware finally caught up. We conquered computational amnesia with the attention mechanism, mapping entire concepts into high-dimensional vector spaces, and we revolutionized parallel processing with the transformer. All of this highly complex, mathematically elegant engineering is running quietly in the background, trained step by step through teacher forcing, just to give you that effortless translation on your screen.
And this raises an important question regarding how we evaluate these systems moving forward.
Yeah.
Because while these models have reached heights that really rival human parity in high-resource scenarios, we have to apply critical thinking to their limitations.
Right.
They still suffer from domain shift. An NMT model trained heavily on, say, parliamentary proceedings will stumble if you ask it to translate a patient's casual text message to a doctor. The semantic vectors shift depending on the domain, medical, legal, colloquial, and recognizing those boundaries is critical.
We just learned that a dedicated NMT model can translate beautifully with just a few 100 million parameters because it was explicitly designed and structured to do exactly that. But today, the tech industry is increasingly relying on generative LLMs to perform those same translations using 175 billion parameters just to predict the next logical word.
A massive shift.
It leaves you wondering, as we move forward, are we actually achieving a better, deeper structural understanding between human languages, or are we just throwing massive, computationally expensive brute force at a problem we had already solved elegantly years ago?
It is a profound architectural debate, and honestly, it's one that will define the next decade of artificial intelligence.
So the next time you highlight a block of text on your phone and hit translate, remember, you aren't invoking magic. You are triggering a highly sophisticated cascade of vector mathematics, self-attention mechanisms, and decades of relentless engineering. Thank you for joining us on this deep dive. Stay curious, and we'll see you next time.